Here we have a contingency table that shows the age group and the type of music that they like. So for example, out of some sample, 50 people within ages 15 through 25 chose rock as their favorite music type. When we have such a contingency table, we can think about the following question: whether the age and the type of music they like are related or not. So we work with the following hypothesis. The null hypothesis is that the age and music type are independent, and the alternative hypothesis is that the age and music type are not independent. So this type of testing is called chi-square test of independence. And for chi-square test of independence, you always have the alternative hypothesis as the not independent one, and the null hypothesis as independent one. And we come up with some scoring system to see how much independence, or how different they are among the age groups. And that scoring system, if it becomes more than certain critical value, then we reject the null hypothesis and say that, oh, indeed, they are not independent. That's like the broad outline of what we're going to do. Okay, so let's look at the scoring system. It's called the chi-square test statistic. So this is our test statistic to, or the scoring system to see how different the ages are and the type of music that they like. Okay, and the O is the observed value, and E is something called the expected value. I'll explain more about this formula a little later. But then along with the chi-squared, you need something called degrees of freedom, which is computed as row minus 1 and column minus 1. And when I talk about the row and columns, it just refers to the data that you have. So exclude these other parts. Just look at where the data is collected. So these are the numbers, right? And you, because this is 3 by 3, you subtract 1 off of each, and then you multiply. So in our case, it's 2 times 2, which is equal to 4. Okay, now back to the expected. So in this formula, expected value of the ith row and jth column is computed by the following formula. You need first the total of this row and total of this column, and you also need the total population, and you compute the product of this total and this total, and then divide it by the total, the grand total. Okay, so let me give you an example. Before we do that, we first need to populate the total column, okay? Because we need these values, right? So you add these numbers, you get 208. You add these numbers, you get 219, and so on and so on. And if you add the total of the totals, you get 668. And the same goes here. You add column-wise, and if you add these numbers, you also get 668, which means that the 668 is the entire sample size. So for example, this E11, first row, first column, the expected value is computed as follows. Its total, row total is 208. Column total is also 208. So you do 208 times 208 divided by the grand total, which is 668. And that's the value, 64.8. That's like the expected. And what this really does is, like, if this was not given, if the actual data were not given and only these numbers were given, and you just assume that it's perfectly independent, then this much would be computed like the following. You calculate what 208 out of 668 is, and again multiply that to 208 out of 668. That would be the percentage that this cell would be occupying, right? And finally, to convert that to the actual number, you multiply this 668, and that's how you end up with this, because the 668, one of them will cancel away. And you would expect 64.8 to fill this spot if these two differences were totally independent of each other. Okay, so let's move on. And one nice thing to do is often people write the expected value as a parenthesis so that you can kind of compare the two numbers. You would expect this much, but the actual value is 50, so it's kind of very different here. So you can do that kind of analysis for the other one. Let me just do one more. So for example, for the E12, the first row, second column, you multiply 208 times 250, and you divide it by 668, and that gives you 77.8 as the expected value. And we just continue on and fill every parenthesis here, so we get these expected value. And then we're ready to actually compute this chi-squared statistic, the sample statistic. This one, you look at the observed data, which is 50, subtract the expected value, which is 64.8, square it, and you divide by 64.8. And you do that for every cell. So you do it for this one as well. 85 minus 77.8 squared divided by 77.8. And you keep going until you reach this last one, which is 77 minus 75.8 squared divided by 75.8. And this value, if you actually did the computation, you will get 12.95. And it takes a while. You have to know what this means. It's this chi-square value being 12.95 means that here's the chi-square distribution. When the degree of freedom is like 1, it actually it looks a little different, but in general it looks somewhat like this. And if this is 12.95, it's somewhat in the high upper region, and the area after that will be quite small, right? And for this type of situation, the p-value is defined as the probability that your sample statistic could be 12.95 or greater. Okay, so what's the probability that this could happen? That's the question. And to do this with your calculator, you need to first convert it like this. So the probability of something getting bigger than a value is 1 minus the probability of something getting smaller. And we can use a calculator to calculate that. Second vars, on. Let's clear this. Second vars. You go to chi-squared cumulative distribution, and lower is kept as 0, and it's not negative infinity because chi-squared can never be negative. So the lower is 0. The upper is what you put here, 12.95. And then degrees of freedom we have as 4. We have it as 4, right? Paste it, and you get this value, 0.98847. But because we want to do 1 minus this value, so if you go back and see what we did, we actually found the area between 0 to 12.95, right? So in this picture, we found the area between 0 to 12.95, but we are actually interested in the area after 12.95, so that's why we have to subtract from 1. So we have to do 1 minus 0.988477, and you get 0.011523. So that's the p-value that we get. Okay, Okay, so what does this p-value mean? It means that this score of 12.95 is rather big. In fact, the chance of getting such a number when this was in fact just independent, the ages and music type were independent, is so low that it's like 1.15%. Okay, so that's this 12.95 has a p-value of 0.0115, or you can say that it has this sample has the significance of 1.15. Okay, and it's less than the significance that we wanted, right? So you said use a 5% level of significance. So since there is only 1.15% chance that such high x squared can happen, we reject the null hypothesis at 5% significance. And let's just clear away some of the things I wrote. Okay, so here's a summary of what we did. We calculated the chi-squared as 12.95 and came up with the p-value as 0.01152, and then concluded that since there is only 1.15% chance, we reject the null hypothesis at 5% significance. But if you recall what the null hypothesis and the alternative hypothesis was, the null hypothesis was that they were independent, but here we now reject H0 and choose the alternative hypothesis and conclude that indeed the age and music type are not independent. So different age groups have different music choices. That's the conclusion from this table. All right, let me add a few more remarks. One remark is that you can actually do all this in your calculator, although it's a little bit more involved. So let me show you how that's done. So what you can do is first go to second and the matrix, and you go to edit and enter, and you put 3x3 matrix, and you can actually put all the numbers here. I already did that so to save time, but you can enter all these numbers just like here. And then once you have that ready, then second quit, go to stat and go to tests, go all the way down, and you'll find the chi-square test, and keep it as observed as A, and B, even if you didn't do anything to B, don't worry about it, just put it as B, and then you calculate, enter. Oh, sorry, that screen was what we wanted. So let me go back, stat, tests, chi-square test. Okay, if you calculate, you can see that indeed it gives you all the values. See, it tells you what the degree of freedom is, and then it gives you the chi-square statistic, which is 12.95, and it even gave us the 1.15% chance. So it does everything. And furthermore, once you run this, then you can go to second matrix and look at what's populated in B, and you'll see that it has all the expected value populated, so that it's automatically populated. So this can save you time, or you can also use this to verify your calculations if you did the calculations in some other way. Okay, still, the last remark I have is that sometimes the questions might be formulated so that they ask you for the critical value, and then you have to figure out whether your chi-squared test statistic lies in the rejection region or not. So in that case, you have to look at the chi-squared table, and because our degrees of freedom was 4 and we're looking at 5% significance level, you can see the value is 9.49. Well, what does that mean? That means that the rejection region is 9.49 and afterwards, and our 12.95 falls in the rejection region, and we can come up with the same conclusion as before. Okay, so there are various things that can be asked. Some questions will ask you for the p-value and ask you to draw a conclusion. Some questions might ask you to find the critical value and draw the conclusion by figuring out whether 12.95 is in the rejection region or not.